Now, continuing with canopy and ecosystem ecophysiology, we're going to introduce the concept of water use efficiency. Water use efficiency is a key concept in levels of organization from the leaf to the globe. Water use efficiency is defined as photosynthesis over transpiration for physiological purposes. I won't give you any of the agricultural definitions right now. I don't want to confuse the issue. So basically, water use efficiency gets higher as stomata start to shut. This is because as stomata shut, transpiration declines faster than photosynthesis does. Thus, water use efficiency goes up because the number below the fraction is going up faster, which means it's getting larger, which means that the fraction itself is going towards zero. We can use water use efficiency to determine hydrologic niche. So here I'm showing you river red gums out in Central Australia. They have a very low water use efficiency. That's because they are groundwater dependent trees and they always have their toes in the water, and so they can operate as if they were getting 1,000 millimeters of rain more per year than they're actually getting. Whereas all the other plants out in Central Australia that truly do only get 300 millimeters of rain a year have that much higher water use efficiency because their stomata close more, which means that their transpiration is restricted a lot more than their photosynthesis. We talked about C3s versus C4 plants. And so here I'm just showing you, reminding you of the Calvin-Benson cycle. CO2 comes in and gets carboxylated by rubisco. And it forms 3-phosphoglycerate. This is a 3-carbon atom, thus this is called C3 photosynthesis. This all occurs in the mesophyll cells. By contrast, in C4 photosynthesis, you get conversion of CO2 into a C4 acid, usually something like oxaloacetate or malate. Then those C4 acids are transferred to the bundle sheath cells, so right around the xylem and phloem, where they're formed back into CO2. They release the CO2, and the CO2 goes through the regular Calvin-Benson cycle, but only in the bundle sheath cells, where that CO2 can be concentrated at much higher levels than they would be in the mesophyll. And this is why when the term Krantz anatomy comes along, this is what Krantz anatomy is. Basically, most of the chlorophyll is in those bundle sheath cells. There is some chlorophyll in the palisades or mesophyll because they still need to generate energy to form the C4 acid that they send off to the bundle sheath cells. But most of the chlorophyll, most of the chloroplasts are in the bundle sheath cells where the regular Calvin-Benson C3 photosynthesis is occurring. The upshot of this is that C4 plants tend to have a much higher temperature optimum because they don't experience photorespiration. They don't have photosynthetic production of oxygen like C3 plants do. So C3 plants tend to have a lower temperature optimum, but also they tend to have lower photosynthetic rates in general. So notice how much higher peak photosynthesis is for C4 plants versus C3 plants.